Alright, so, what does Boyle's law state? No. That's ideal gas law. No. Oh yeah, you're right. I think 25. No, 20. So, you need to know it in words. New. So, I want to be able to look at the test at the same time, look at what I'm putting on the screen. You can, yes, I am putting it in, and you can correct it if you come after school. Or if you find a period, or during lunch, or during my conference period, fifth period, or so during lunch you can correct it, or if you can somehow get out of 6th, 7th, or 8th. So, how I remember the gas laws is using the mnemonic. Can y'all see that? Boyle plays video games. So that means Boyle law, and let me turn this. There we go. So Boyle law is pressure and volume. And it's P times V equals some constant. And if we look at P, if P gets, so let's plug in some numbers. Let's say that this constant is equal to 4. And let's say that pressure is 2. What would have to be volume? 2 times what equals 4? 2. So, looking at this, if I increase pressure up to 4, what must happen to volume for K to stay 4? So, if I increase pressure to 4, what must happen to volume? So, 4 times what is equal to 4? 1. So, if I increase pressure, from 2 to 4, volume had to go down. So, in other words, Boyle's law states that as pressure goes up, volume must go down. In other words, pressure and volume are inversely related. So now let's look at Charles's law. So Charlie Brown was a TV show. So Charles's law, so it has a TV in it, is about temperature and volume. So remembering the combined gas law, in it we have volume on top and temperature on bottom, and that's equal to some constant. So let's plug in imaginary numbers. Let's let our constant be 4. Let's choose an arbitrary value of 4 for here. So 4 divided by 1 is equal to 4. What happens if I take 4 and increase it to 8? What must temperature be so that this is still equal to 4? So 2. So in other words, if volume increases, what temperature must do? Temperature must, it went from, so if I increase 4 to 8, the temperature went from 1 to 2. So it increased. So if volume increases, temperature increases. So if volume increases, temperature increases. I'll actually come over here and just say that. If volume increases, temperature increases. This means that temperature, or volume and temperature, are directly related. So again, Boyle's law, you can remember it by Boyle plays video games. So play and video, pressure and volume. You can remember if it's inverse or direct by just working with some values and seeing what happens. So let's look at the last one. Okay, Lassac uses TP on the maypole. So in other words, Gay-Lussac's law is about temperature and pressure. So going back to the combined gas law, we have PV over T. So removing the volume, pressure divided by temperature is equal to some constant. So again, we can make up values so that our K be just some value 4. Note, this is the same thing as last time. So I could have 4 divided by 1. If I increase, increase pressure, the constant's going to have to stay still. So if I increase pressure from 4 to 8, we get that temperature must go up. So if I increase pressure, temperature goes up. So if pressure increases, temperature must go up. So if one increases and the other one increases, that means it's a direct relationship. So pressure and temperature have a direct relationship. Instead of saying direct, another thing I can do, I could have worded this also as pressure and temperature are proportional to each other. And going back up here, I could say that pressure and volume are inversely proportional to each other. So you can either say this is inversely related, inversely proportional to, you can say it's directly related, or proportional to each other. Does that make sense? So you need to know about the three main gas laws. You need to memorize the combined gas law. So combined gas law. P times V over T is equal to some constant. You can also remember P1 times V1 divided by some T1 is equal to P2 times V2 divided by some T2. Because they're constant, they'll stay constant. So the before PVT is equal to the after PVT. What is this number called? 6.02 times 10 to the 23rd. This is Avogadro's number. Need to memorize it. And again, in this class, I teach it with 4 significant digits. What does STP stand for? Standard temperature and pressure. So let's look at standard temperature. What is standard temperature? What is standard temperature? In Fahrenheit, it's 32 degrees Fahrenheit. In Celsius, it's 0 degrees Celsius. And in Kelvin, it's 273.15 Kelvin. Nope, Kelvin doesn't have a degree symbol. I don't think I saw anyone using it yet. But if you put degrees Kelvin, that is wrong. So basically, standard temperature. What are these values? What do all these represent? Temperature. What specific temperature? What's at 0 degrees Celsius, 32 degrees Fahrenheit? Freezing point of water. Surely, I know. We at one point did it, but we at one point went to the metric, but we made it optional. And the states went, so it's optional, and you suggest that we go spend millions of dollars replacing all the signs? I think I'm going to just keep the money. And we never did it. We did change it, but we didn't make it a law that everyone had to go change all the signs, and so we never did. So, let's look at standard pressure now. So, standard pressure, what is standard pressure? What value is standard pressure at? 1 atmosphere. And what about in other units? 760 millimeters mercury. Yeah, I don't think that's going to be able to test. The other one is kilopascal. No, it's not. 101.1325 kilopascal. So, what do these values represent? What pressure, though? So here, when I asked about standard temperature, I asked what does these represent? What is the thing? And it was the freezing point of water. So what is this pressure? What's something common? Pressure at sea level. So they took standard temperature and standard pressure and they made it based off of two things we know. We know what pressure it is at the beach. We know what the freezing point of water is. Hence the reason why we define the standard based on them. Note, you don't need to know this for the test. So, but these are the pre 1982 standard STP. So note, these are the old pre-19 STP values. You don't need to know this. Oh, I was for continuing. What is standard volume? Maybe. What is standard volume? I never really said this. I never really called it standard volume. But what was the standard that we used? So when did we use volume at STP? When did I say something has a volume at STP? .4 liters, i.e. the volume of 1 mole of gas at STP. This value is known as standard volume. I never told you the name of it. But it is called standard volume. Let me derive that real quick. See if I can do it super quick. So we have a pressure of 1 atmosphere. We have R. I'm going to have to get a more precise value of R. R gas value. Where's atmospheres? There it is. R is 0.082057366080960 liters atmospheres per Kelvin mole. Again, you guys on the test will be given as 8.21, but see how off it is? It's not very precise. So standard standard temperature is 273.15 Kelvin. Number of moles is 1 mole. So we take the ideal gas law, nRT, solve for volume at STP. Volume is equal to nRT divided by P. If I plug all these numbers into this equation, we can get standard volume. So 1 mole times whatever this R was, I'm not rewriting it, times 273.15 Kelvin divided by 1 atmosphere. Times 273.15. I get a value of 22.4139695 liters. Which, again, for this class, some of these values are rounded to only 2 significant figures. It rounded it to 22.4 liters. Note that if I used this value of R with only 3 significant figures, so 0.0821 times 273.15, so right here. If I use 0.0821 and I times it by 273.15, I get a value of 22.425615. It's still accurate to 3 significant figures. But that's how they came up with that value. So again, these are pre-1982 values. Do y'all remember what the current, again, you don't really need to know it for the test. But do y'all remember the current values of them? So all they did well, they didn't do anything with temperature. They just changed the atmosphere to use pascals, 10 to the 5th pascals. So our 100 kilopascal, our 1 bar. Let's see if we can find volume on here. Molar volume. So 22.414 using the old definition. If we were to use the current definition, it would go up to 22.7. But these are standard values that they use. So So for the current for the one used in this class, 0 and 101.325 kilopascal, we do the 22.4. But even if you didn't know, if you totally forget what 22.4 is, if you totally forget, do note that you can use ideal gas law, volume equals nRTP, for 1 mole at temperature, standard temperature, standard pressure. Plug in your R value, you come out with standard volume. So you get standard volume. But we are going to use the ones taught in my class. Know how to convert between grams and moles. Know how to calculate molar mass. For example, of water. Water is H2O. We have 2 times H. 1 times O. So that would be 2 times 1.00. Is it 2 or 3 zeros? So it's 2 zeros. And 1 times 15.9994. And that tells us that the molar mass of water is 18.0152 grams per 1 mole. So know how to calculate molar mass and how to use it to convert moles to grams or grams to moles. Going back up here to these gas laws, I would like to add, know what they mean. For example, if you heat up a metal can with gas in it, what happens to pressure? But I'm asking what happens to the pressure. If you heat up a metal can with gas in it, what happens to the pressure of the gas? So what happens? It increases, so the pressure increases. You do. This would be, so this is pressure and temperature. So pressure and temperature is Gay-Lussac's. So there are going to be a few questions where I give you a scenario and you need to predict what will happen based solely on these 3 laws. They don't give you these laws, you need to memorize them. There will be several questions that use combined gas law, which I already stated, the combined gas law and several questions about ideal gas law. So P times V equal to N times R times T are written more cleanly. So you're going to have to memorize these two equations and be able to use it. So what I'm giving you on this test, we'll just copy and paste it from the test. So this is copied and pasted from the test. That's all I give you. 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 101.325 kilopascal. Yes. Here's your first R using atmospheres. That is equal to this, which is equal to that. Everything else you will have to memorize. I do give a periodic table attached to the end of the test. So you need to know STP, because some questions would be like, so a gas is at 5 atmospheres, 25, let's do 100 Kelvin, and is in a 2-liter bottle. What is the volume of the bottle at STP? Would you mind closing the door? So not only do you need to know the combined gas law, you have to know STP to solve this problem. What do you mean? So this example. So initial pressure was 5 atmospheres. Initial volume is 2 liters. And initial temperature is 100 Kelvin. Also, know how to convert between Celsius and Kelvin. Most of all these problems are in Celsius, some are in Kelvin. Some will ask you to convert back into Kelvin, or convert back into Celsius. I do not use Fahrenheit on the test, so you don't need to know that. So our final pressure is STP. So STP is 1 atmosphere. We use atmosphere because there's atmosphere over here. We're solving for final volume. And this is in Kelvin. STP is this. So, initial pressure times initial volume over initial temperature is equal to P2 V2 over T2. We're solving for final volume. So it's being divided by T2. So to move it over here, I'm going to multiply by T2. That gets rid of it on this side. It's being multiplied by pressure 2. So I'll divide it on this side, P2. And that gets rid of it on this side. So volume 2 is equal to temperature 2, P1, V1 over P2 T1. Now you just plug it in. Make sure you plug the correct values in to the correct spot. And I made a mistake. That should be volume right here. Again, if you use units, it will help you find errors. So pressure 2 was 1 atmosphere. Temperature 1 is 100 Kelvin. Plugging that into a calculator. I get 27.315. So Kelvin cancels out. Atmospheres cancel out. And it's liters. So in the example where I gave you that you're heating up a metal container, you're going to have to use some common sense. Do you think that if you had a Coke pan that's just full of air and it's completely sealed, do you think if you heated it up, it start acting like a balloon and swelling? No, you should use some common sense. Really think, would the volume actually change if it's metal? So what would happen if I heated up a balloon? Do you think the pressure inside the balloon would go up? Yes, technically, slightly. But more than likely, what would happen is the pressure is going to stay the same, and the volume is going to change. Because rubber is more flexible. Rubber can't contain the pressure. So the pressure is going to try to be the same as atmospheric. So when you blow up a balloon, the rubber is able to stretch out and maintain, so the pressure inside the balloon is the same as the pressure outside the balloon. That's the reason why it changes its volume. So if you increase volume, what happens to temperature? Do y'all know how like a can of deodorant works? Do y'all know how a can of deodorant works? Have you ever jiggled it around? What does it sound like inside? It sounds like air? Yeah, that's what I was supposed to say. Do tell. I'm thinking of Disney, The Sound of the Wind. All, what do you hear inside of a can of deodorant? That's more like paint. They usually don't put it in deodorant. But it doesn't sound like it's like liquid. No, it's a mixture of. But that's the point I'm making. There's liquid in there, right? But it don't sound like it. It's because it's under a high amount of pressure. So in a can of air, our deodorant. So in we don't get to this now. I just wanted to illustrate to you guys that the pressure inside of a can of air, a can of deodorant, a can of hairspray is under so much pressure that the is under so much pressure that the gas starts becoming a liquid down below. So what you have is in a can of air is you have it's mostly gas, but it's under so much pressure the gas becomes a liquid. Are you saying that the water down below is not liquid? So, if you squeeze a gas really, really hard, you can eventually cause it to turn into a liquid. But when you start using, so there's a straw connected down here into the liquid. Whenever this is under high pressure, several atmospheres of pressure. Whenever this gas comes out, the liquid is going to immediately turn back into a gas. So when you're using a can of air, what's happening to the volume inside? So when I say volume, I'm only referring to gas. This whole unit is gas. What is happening? So as this liquid gets less and less, what happens to the volume of the gas? It's increasing. So the gas volume increases. Um, Hold on, this doesn't make sense. I might remove this problem because I made a bad analogy. Yeah, I made a bad analogy. I'm just gonna. I'll let y'all decide what the correct answer should be, but I'm not gonna rate it against y'all if I got it wrong. No, because this is 25% guess. So we know from looking at volume and temperature. If volume increases, temperature increases. But after you use a can of deodorant, if you were to hold down a can of air, you would actually see ice form around the can. Yes. Deodorant doesn't work too well. A can of air works the best. Yeah, yeah. They can work very good. Be careful as literally, whenever it comes out, it doesn't immediately turn back from a liquid to a gas. Sometimes they can spray super cold, like negative 50, negative 100 degree Fahrenheit liquid that can instantly freeze your skin and give you frostbite. But my point was, this is wrong. The way I was explaining it. Anyway, the code word of the day on the screen. There's the code word.